The final part of that last free response question we just tackled and polished off was concerning the Lagrange remainder, a topic I know from experience a lot of students find both confusing and intimidating, so it bears review for sure. Let's take a look at Taylor polynomial. If a function f is differentiable through order n plus 1 on an interval I containing c, why do we need n plus 1 derivatives? Well, because it's sort of like the alternating series remainder where you just look at the next term. We're going to do also the first neglected term. We went up to n terms in our Taylor polynomial. We're going to look at the very next one, the n plus 1. So we have to be able to take n plus 1 derivatives at least. All right. Then for each x in your interval, there exists z between x and c such that, so c is where your Taylor polynomial is centered. You can see that in each one of those parentheses. And your x value is the number that you're sticking into the Taylor polynomial to approximate your function. It's the x value that's in each one of these parentheses. So we're finding a z value in between there. And take a look at the function here. F of x is the function in question. Everything that follows, this is essentially a Taylor polynomial, not exactly a series because it doesn't go on forever, and it's an nth degree Taylor polynomial. That's not exactly equal to your function. There's a little bit left over, which we call that remainder at the end of it. And then here is the Lagrange form of this remainder. There's a couple of different forms. This is the only one that we're expected to know on the AP Calculus exam. So the remainder says basically you can look at it. It looks just like these things here, the terms in the Taylor polynomial, except for we're looking at the next one. The key difference here in this Lagrange form of the remainder is that it has a z that we're evaluating our n plus 1th derivative at instead of c where we are centered. So let's talk a little bit about this z value, which again is in between our x value and our c value someplace. It could be x, it could be c, it could be some number that's in between there. Specifically, it's the number that maximizes that n plus 1th derivative. All right, and again, that x value is the value that you're approximating your function at. So take a look at some pictures over here on the margin. We have the n plus 1th derivative graphed for us. It's not the absolute value of it. It would take the piece that's down here and reflect it up over the x-axis, of course. That's not going to come into play over the interval that we need. The interval that we need is all positive, so who cares about the absolute value? Here's where we're centered at c, and then let's say, for example, we are trying to approximate our function at on our x value. On the interval that contains both of those points, we can see that our n plus 1th derivative is increasing, and so the maximum value happens at c, so I'd select that one. All right, that's not the only case. Let's look at the next one here. This time the maximum value occurs at x. Again, on the interval that contains both the c value, the center point, and where we're approximating at x, that interval, the n plus 1th derivative is increasing, so we're going to pick the one that's on the right-hand side. In this case, it's the x value here, so we would select that one. All right, that's not the only thing that could possibly happen. Sometimes some more complicated things occur, and we're looking for the maximum value one more time. Like I said, it bears repeating. The maximum value on the n plus 1th derivative, and that z value is someplace in between our x value and our c value. We've got one more picture right over here in the margin. So this time on the interval that contains c and x, you can see that your n plus 1th derivative is not strictly increasing or decreasing. It goes up, comes back down. The maximum value is someplace in between here. So really, to find that value, you'd have to take, say, another derivative, find a critical value. It's this whole optimization process, which is something we absolutely don't get into here. So most of the time, we just find a number that is good enough to approximate that, some reasonable boundary point for our n plus 1th derivative. And we're going to get that either from a graph or from a table of values like we did from the previous example, or maybe they give us a function that we could have found the n plus 1th derivative for, and then maybe it's increasing or decreasing. We choose the left side, we choose the right side, or whatever on that function. And we've seen some examples like that before. So in our last example, not only for this lesson, but for the entire unit, we have, suppose f is equal to the sum of its Taylor series for all values of x. The graph of y is equal to the absolute value of the fifth derivative of x is shown at the left. All right, so since this is absolute value, chances are there was some part of the graph down there and I reflected up above. Okay, so let t sub 4 of x be the fourth degree Taylor polynomial for f about 0. So technically this is the Maclaurin. But you know what? I call mine Taylor series 2 anyway. Who's going to give that Maclaurin guy all his dues? Who knows? Not me. Use information from the graph to show that the absolute value, the difference between t sub 4 of 1/4 minus f of 1/4 is less than 1 over 6,000. So in this case, it doesn't tell us Lagrange. Sometimes it does. That's what the last one did. But what it does do is give you a number to shoot for. All right, so let's look at this part in particular. Let me remind you of something, like where it came from, so that you know exactly what it is that this thing is looking for. So we started off with a function, and we approximating that function with, in this case, a fourth degree Taylor polynomial. It's not exactly equal. To make it equal, I would have to add a little bit of extra. That's the remainder, that's right there, the remainder function. And then it is exactly equal. And now if we solve this equation for the remainder, all we'd have to do is subtract our Taylor polynomial from our function, and we would get our remainder function. Okay, now this could be positive, it could be negative, it just depends on which one of these things is bigger. So we take the absolute value of both sides of this, and that gives us the error. Now, since we're taking the absolute value, it doesn't matter what order this comes in. So if you think of, let's say, the distance formula, which has x sub 2 minus x sub 1 in it, it didn't really matter which one's x sub 2 or which one's x sub 1 because you're going to square that and make it positive. Same thing's going to happen here. It doesn't matter the fact that they have these things switched around. It's still the absolute value. It's still the same exact number. So really, in essence, whenever they write absolute value t sub 4 of 1/4 minus f of 1/4, we're finding the remainder. And since this is a Taylor polynomial, we're going to use the Lagrange form of that remainder, which is less than or equal to the next term. We went up to 4, so we're going to go to the fifth derivative, not necessarily evaluated at 1/4, no, the center point, right? Center point is where you usually evaluate all those derivatives, in this case 0. This one is going to be at some value, z, and remember that z value is someplace in between 1/4 and the 0 where we're centered, over 5 factorial times x minus c, but our c value is 0, so x to the 5th power. That's a 5, guys. See, look at that, it's a 5. All right, and we know what that x value is. It's the thing that they gave us right here in the parentheses. It's 1/4. So let's put that in there. Times 1/4 to the 5th power, absolute value. Under no circumstances is this a safe stop, because we haven't even done the toughest part of this, which was to find the maximum value of the 5th derivative, max. And in this case, we're going to get that value from the graph that they gave us. So let's take a look at the graph. So the graph looks like it's going up by 0.25, which is handy for us because we need to find the maximum value in between x equals 0 and where we are approximating it, which is x is equal to 0.25. So in other words, we just need to find the maximum value of this n plus 1th derivative from 0 to 0.25. And then we can see, of course, that the n plus 1th derivative, or at least the absolute value of it, is increasing on that interval. So I would choose the right endpoint, which is right here. And who the heck knows what that value is? Something that's less than 20. I don't need to know what it is. I'm just going to check, and I'm just going to pick the most convenient value, which in this case is 20. I could pick something up here, but that didn't make sense. Why don't I just use 20, which is, I can definitely visualize that it's more than the value that I need, and it's pretty close to it. So it is a reasonable bound for our error. So 20 is the number that we're going to use for our maximum value. And now, strictly speaking, this is now less than, not less than or equal to, because we picked a bigger number here. Absolute value of 20 over 5 factorial, which is 120, times, I'm just going to rewrite that as 1 over 4 to the 5th. Now, I would also recommend not safe stopping it here because we have a number to shoot for. We want to show that it's less than this 1 over 6,000. So we have some more arithmetic to do, but who doesn't love arithmetic? So absolute value is contributing nothing at all to this problem at this point, so let's get rid of it. 20 over 120 times 1 over 4 to the 5th. And then let's do some cancellation. Like we can cancel out these 20s right here, right? No, I'm just playing. But we can cancel out the zeros. And let's see, 2 goes into 12. I wasn't going to erase that. Come on, I just wanted to cross it out. Goes in there 6 times, so 1 over 6. All right, so what we got so far then is 1 over 6 times 1 over 4 to the 5th. Now all we got to do is multiply these numbers together without a calculator. So the toughest part of that is that 4 to the 5th. So you could just go 4 times 4 times 4 times 4 and all of that, but I'm going to think of it, I'm going to break it up into some easy chunks, like 4 squared is 16, times 4 squared, which is another 16, and then times a 4. So 16 times 16 is 256, and now I just need to multiply that times 4. So let's pretend like we're on the 4th or the 5th grade. It's one of those, I'm not sure. Let's ask Rowan. And do some long multiplication. Is that what it's called? Long multiplication? It's whatever. All right, so 4 times 6 is 24. 2, 20 plus 2, 22, carry a 2, that's 8, plus 2 more is 10. Nice. Now we just have to multiply it by 6 right there. I've got a pretty good feeling about this if you stop freaking out on me. So multiply that times 6. You get a 24. Carry a 2, 12 plus 2 more is a 14. Carry the 1. That'll be a 1, and 6 times 1 is, and we are in business because that's our denominator. That is 1 over 6,144, which is less than 1 over 6,000. And we did it. We pulled it off, right? That's all you got to do, and that justifies that we didn't even have to justify, we just had to show it, and we did. We did all the calculation to show that we could force our remainder to being less than 1 over 6,144, which in turn is less than the number that they gave us, so we're in business. So that concludes our lesson, guys. It concludes also the whole entire unit. This is what we were aiming for this whole entire unit about series. So we wanted to be able to represent our function with some Taylor and Maclaurin series, and there's lots of applications why you'd want to do that for approximation reasons. And the way that we tackled those problems is we first started with a whole bunch of derivatives. We plugged in our center point, wrote the terms of our series, and then try to find some sort of pattern so we can generalize that and write it as a summation. However, we don't always want to do that, especially since it's fairly tedious and time consuming. So we want to have a couple of key ones absolutely memorized. We want to have like the one for the geometric, 1 over 1 minus x memorized, e to the x, sine of x, cosine x, natural log of 1 plus x, because when we have those ones memorized and they throw them at us, we don't have to think about it. And we might be using that in combination with another function, multiplication, division, composition, in order to make a new Taylor or Maclaurin series that they give us. Anything that they choose to throw at us. And there you go, folks. You guys are on the fast track to getting a 6. That's right, a 6, not a 5, a 6 on the AP exam.